The background actually for this study is not in accretion disk community, because we were doing convection simulations with the stellar context in mind, because turbulent convection is expected to occur in the outer layers of late type stars, such as the Sun, and also other places, but this is what we were mainly interested in. And this convection then usually drives the large-scale dynamo. So we see large-scale magnetic fields in the Sun, and people have been trying to discover or to find large-scale dynamos in convection simulations, which has been proven to be quite difficult. And there's a few reasons to that. And one of the reasons is that there is no large-scale shear present in these simulations usually. Among other things, and these other things are so difficult that we are not even trying to address them, so we address the easy thing first, which is adding shear flow. One of these other things which is likely to be important is the lack of scale separation, so we need to have a huge resolution in order to have enough scales in our simulations to be able to generate large-scale magnetic fields without shear. So what we then do, we just have a Cartesian box full of ideal gas, and I will show a picture in a moment of this, so it will become more clear. And we apply the shearing box approximation in order to impose a linear shear flow. This form, and then we solve just the usual MHD equations: continuity, induction, momentum, and then energy. And here we use explicit viscosities, so there's no hanky-panky with hyperviscosities. And what else should I say here? I think that's enough. So the model looks like that. So we have a piecewise polytropic stratification. So we have a lower layer which is stable, which is characterized by polytropic index 3. Then we have a convectively unstable layer where polytropic index is equal to 1, and after a while you get this turbulent convection going on there. And
Patrick, in your previous equation, you have a relaxation of the, that's the way you get convection. You have relaxation of the entropy.
You mean this term?
Yes.
This is actually the cooling term on the top. So we keep, there's actually a third layer on top where we remove heat because there's a constant heat flux from below. So we want to get into some kind of equilibrium after a while. So that's why we remove heat from the top. And then we just have a constant gravity here, which is different to having to the accretion disk case usually, where gravity depends on the z coordinate, which is not the case here. And there we just have the usual parameters for describing the large-scale flow and rotation. So we use the Q parameter here, which describes how the angular velocity depends on radius. And with our parameters omega and s, we can represent it like that. And the only parameter that should be kept in mind during this talk is this one, what we call the Coriolis number, or the inverse of the Rossby number. And this describes essentially the strength of convection, or strength of rotation in comparison to advection. And what we then do is to put in a weak magnetic field, a random field, and then just wait a long time in real time. I mean, much longer than what it seems here. And okay, we should be able to see something now. So first of all, this is the highest Reynolds number case, or the most turbulent case we have done so far. And initially there's only small-scale magnetic fields that you see developing, and this takes usually quite a long time, hundreds of turnover times. And when we are patient enough and wait even longer, then we start to see large-scale magnetic fields generating. So I will let the animation run in the background. So this is what we get for the, this is the streamwise and this is the cross-streamwise component of the magnetic field. And this is now averaged over the horizontal direction, so it depends on the Z coordinate. So after a while we see that there is a large-scale magnetic field generated. And this is actually quite a strong field, because compared to the equipartition strength of the magnetic field, this is basically the turbulence intensity. This is super equipartition. And this particular run was made with Q equals 1. This is just an easy choice to have the same shear parameter and rotation parameter, and then in this definition the correlation number is of the order of 1. And now this, of course, to many people I think this will ring some alarm bells, that this has to be the MRI which is doing all the work here, because we have Q which is favorable, and then we have magnetic fields in the system. And but the disappointment to those people is that we can see a very similar dynamo if we switch off rotation totally. And we see a very similar time evolution, and we have been able to find out, or this is actually not only in convection but also in force turbulence, that the growth rate of this dynamo depends on the shear parameter. It's linearly proportional to the shear parameter.
So I'm confused, but you started this talk by saying that you don't see dynamos in conductive simulations, so...
You don't see dynamos in conductive simulations without shear.
Without shear. And so Q equals infinity, sorry, that corresponds to...
Omega 0.
Yeah.
So now there's...
Only
well,
shear.
there's no Coriolis, but there's still shear. There's linear
yes,
shear.
exactly.
Got it. Sorry.
Yeah.
Okay.
So, okay. Now the next figure, I didn't know where to put it, so I put it here. So you see here that this is the RMS velocity in the simulation, and then magnetic field which grows after only quite a long time. And I just want to show this picture here because we can then pick out two regimes or two different states from this dynamo. So first of all we have the kinematic stage where the magnetic field is weak, and then we have the saturated state where the magnetic field is saturated. And this is actually where Ramesh comes into the picture. I was visiting here in June, and he was visiting here as well. And I was showing him one of these animations, and he pointed out that, well, this is kind of like a part of an accretion disk, isn't it? And I said, well, yes, it is. And then he just asked, have you looked at the stress? What is the sign of the stress? And I said, well, I haven't looked at it. And I never really thought about it before that. And this is partly because of one paper that was published about 10 years ago by Stone and Balbus, where they do also shearing box simulations of convection, or they have convection in shearing box. And sometime in the middle 80s, when I was doing my master thesis, I was doing MRI, and I remember reading this paper, and they were saying that it's impossible to have the correct sign of the angular momentum transport if you have convection.
But this was not magnetized.
Yeah, this was pure hydro, yes.
So there were even Stone Ages, not Middle Ages,
Well, okay.
which you are apparently unaware of.
Yes. So maybe this was stuck in my mind, so we never looked at this. seriously, and then I started to look at this paper, and this particular statement then stuck to my mind. How can you have inward transport if you have solid body rotation, so you have no shear? And this is actually something that even we did with these convection simulations. And this is a bit puzzling, because to lowest order you can write the Reynolds stress being proportional to your rotation rate, and then you have to have some kind of anisotropy of the horizontal velocity components. Either you have the magnitudes are different, or then the scales in which they vary are different. And this is hard to imagine, at least for me, how you can achieve this if the rotation vector and gravity vector are pointing at the same direction. So these first two papers are analytical studies, and the rest is numerical convection simulations. So the possible explanation is that they just didn't run the simulation long enough, because this thing varies like hell all the time. So if your time series is not long enough, you may get a residual value, which is strictly not zero. But okay, so if we go to the case with shear, they do a parameter study of one point, which we here want to improve, or to study the parameter space a bit more thoroughly. So as a first approximation, we keep the same setup and just vary Q, and then see if the relative strength of the convection, does it matter if we change the Coriolis number, keeping Q constant.
Without magnetic field?
Without, with and without.
Okay.
So here are some examples. So alpha, I have now several different alphas here, so I contribute to this exponential increase of citations to Shakuras and Yaya. So first of all, we have alpha kin, so this is kinematic alpha, or the hydro alpha in the kinematic regime, and kinematic alpha in the saturated regime, and then magnetic alpha in the saturated regime. And here's the total. So here's now two different sets of calculations, one with relatively slow rotation and one with faster rotation. And what's clear from this plot is that for slow rotation, the stress is always positive, which is the opposite what is found by Stone and Balbos. And if we increase the rotation, then we increase actually both, because Q is kept constant, and we increase both shear and rotation. If we increase this, then we actually see a change of sign. And if you look at these values for alpha, you see that they are extremely small, but this is just because I'm being neoconservative with the normalization, so I have just the biggest value of the sound speed that I can find in the box here as a normalization. And then when we go to the saturated regime, then we see that the magnetic stress is much larger always than the kinematic one. And with this normalization, we get alpha parameters of something like 5 times 10 to the minus 3, which is not very impressive. But if we...
Is there any significance or concern in that drop? Oh, I guess that's just Q, so I don't know, like it turns over there.
You mean the last point here?
Right.
Yeah, there was... You get some trouble when you go near Q equals 2.
But the magnetic stresses, we know, go down for a large Q, right? Dashed line was magnetic stress, so they should be, it's normal that they go down. It's just that they go down extremely sharply. If you had one more point or something, a few more points, it would look more smooth. But I think back in '96, Marek and Lasota and I had this already, something like that. Must be.
This was for MRI.
Yeah, sorry. Ah, this is convection, of course, yeah.
So
I remember these stone ages which I've mentioned, and that is Bogdan Paczyński, whose point was that convection transport angular momentum from place to place. So these convective elements are conserving entropy and angular momentum, taking from one place to another place. And therefore it is not difficult to imagine that they will be transporting angular momentum inwards. And I think that you may do very complicated models, but that is, at the end of the day, it is what it does.
Do you agree with that actually? Not quite, I think, no.
Or maybe
Because for,
you want to finish?
Well, I should maybe finish. So here we see, this is actually this point from here. So I use here a different normalization with the local sound speed, and then you get values which are 1 order of magnitude higher. And this is now where the convection zone actually is between these two dotted lines. And the magnetic stress is much larger than the kinematic one. It's about 1 order of magnitude difference. And okay, here's just 5 data points for Keplerian case, with just the Reynolds part of the stress in the kinematic regime. So we see that when rotation is not that strong, then you get positive values, and when you get to high enough correlation number, then you get a change of sign. And
that was Q equals 1, right? Maybe?
no, that's Q equals 1.5.
1.5.
But the magnetic stress is always positive.
That's always positive.
Right.
But was it not 0? I mean, was there no, was that this magnetic field? No. 0 magnetic field, right?
This is in the kinematic regime of the.
So it's 0 magnetic field.
Right, right.
But in general, the magnetic stress is always positive.
So the stone and bulbous point is the very one to the right.
Just
Of
wait
Martin.
a second. So then we actually reproduce their setup, and then we use a different kind of gravity, which is linked to basically the rotation rate here, and then we also consider the possibility that these two, the epicyclic frequency and the rotation frequency, are not the same. Then we do a similar plot. So this is stone and bulbous point here. So instead of 1 point, we have now 6. So I guess this is an improvement of sorts. And here also we see that when we go to something like, this is 4, this point, and the epicyclic frequency is 4 times larger than rotation frequency, then we have a change of sign. And this is not usually the case that these two are different, but apparently it is possible if you are close to a black hole. And okay, there's another way to do this, but this we haven't tried yet. And here I just show 2 different simulations. These are actually the extreme points. This is new epicycle over omega equals 1, and this is 10. So you see that there is a really big difference to the appearance of convection. And this is actually all that I had. The conclusions are self-explaining. Thanks.
Questions?
Do you agree in magnitude as well as sign with the stone and bulbous 1 point?
The magnitude is actually, it's fairly close. So I believe that we do reproduce their results.
The sign, of course, is correct.
The
So
sign
it's
is
negative.
Yeah.
Do you have ux squared versus uy squared? The relative strength of the radial motion versus azimuthal motion?
A plot of that.
Hmm?
You want to see that?
If you have it, or if you have
I
the
don't have
numbers.
it. I can show it to you later.
Okay. Because I think that it is, as Mark said, it's easy to get inwards angular momentum transport with radial forcing, and you'll get outwards without zenithal forcing. So if your convection is providing you with vertical forcing, you then wonder how that gets converted into radial versus azimuthal motion. And I think most of your variations were suggesting that as the rotation slows down, you get much more, should I say, as your rotation slows down, you get less forcing towards radial motion. And so you expect more easy outwards angular momentum transport.
So if you showed the Rüdiger formula again, then it becomes more obvious, I think.
Right, yes.
Yes. So I think that's what you agree with, right?
Yes.
So then the question would be, of course, what's the relative strength? Does the sign of this formula also change at the same place when the actual stress changes sign?
That I haven't looked at.
Because that's, of course, an approximation here.
Yeah. Yeah, and it's also that it's not only the magnitude, but it's also possible that the scales are different, and you can have this relation.
Yeah.
So, and I have a couple of questions. So basically you find that in the purely hydro case, or you go kinematic, but the purely hydro case, in an accretion disk far away from a black hole, where you could actually break the degeneracy between epicyclic and omega, it is true that having convection will not provide the right sign for angular transport. Is that?
Yeah, that's.
Because I'm trying to summarize
Yeah.
in my mind the implication.
That's the implication of this figure. But
So
then there's also the question of, I mean, the convection is basically forced by the amount of heat which is coming from below.
yeah. So there's a consistency.
So, yeah, it depends then on the forcing basically.
Yeah.
If the forcing is high enough, then you can have, you can reduce the correlation number by increasing the convective velocities. But we haven't really experimented with this yet, and it's not really sure that we can actually increase the forcing so much that we can change the sign. That's
Well, there's an issue of consistency, because you need some transport to dissipate energy so that you have this flux. So you need something else acting in the bottom.
yeah. This is an external
Yes.
heating, so it's not really, in that sense, it's not self-consistent.
But there are what we think are MRI unstable disks, which, if you do the relative transfer, have very large opacities and would also be convectively unstable. And so I think there it's interesting, because you're suggesting convection might be more important than the MRI, maybe, because you have a regime where the two could be operating, right?
Yeah, it's in principle it's possible that both are operating. Yes.
Including in some of your simulations.
Yes. It's really difficult to know because
What's going on?
Yeah, because we start with a field. If we have a stable stratification, MRI will not develop because the field is so weak that you can't resolve the wavelengths which are unstable. And but then you get convection going, and then you get application of magnetic fields and.
But on that point, if it is ionizing, you do have magnetic fields. Am I right in still concluding that the magnetic part of the stress will always be positive? Even if there's no MRI, the magnetic fields that you're building up in this convection will always lead to a positive stress, simply because of differential rotation or the shear that always.
Yeah.
So, and that's always dominant over this, over the Reynolds stress?
Yes.
Okay. So you never get negative transport if you have magnetic fields in an ionized system.
Yes.
Yeah.
Of any significant strength.
Yes.
So the regarding this consistency business, I think there's another factor, of course, which determines whether or not you have convection. I mean, on the one hand, you have to put in a certain amount of heat, which you can express in terms of an alpha, because you could estimate that the amount of heat input is equal to the turbulent viscosity times the shear squared times 3 halves squared times the density and maybe a factor of 2 or something. So that would be the input. But on the other hand, you also have a loss, of course, and that depends on the opacity. And I think you raised this
That's
issue
what
already.
goes on in all these models.
Yes,
essentially,
exactly.
where you
So if
can-
you have if the opacity kicks in rapidly enough, all of a sudden, you will always have convection, I believe. Even with
that
the
depends on the disk. So for instance, this is an interesting
at
question.
least
For
it could
instance,
be a
Tintori-
manufacturer such that
Tintori disks,
yeah.
you can do all this, put the opacities in, put some alpha, 10 to the minus 2.
Mhm.
You find that they are non-convective anywhere. That's a basic result, which is not true of these other disks there. So there, the macrophysics matters.
Mhm.
Given the opacities, because the opacities are low basically here in
Mhm.
this range of temperatures, and they can be high here.
For the-
That's for the
Right.
ionized, you know.
Yes.
The opacities get very high at 10 to the 4 Kelvin. They get very low at 10 to the 3 and below, basically. That's what I'm saying.
So protoplanetary disks, you say it would work?
Well, I think the trend claim that I've seen, and I sort of explain why, is that the opacities are low and you don't find
Mm.
much convection. Maybe something at the inner edge, but in general, it's not clear that how they would be convected. Within an alpha model, I guess.
Mhm.
There is an issue with initial condition. You know, it's chicken and egg here.
Mhm.
You put alpha to get energy release, and then you ask, what do you get? But you don't have energy release if you don't have viscosity, and you don't have your alpha. So it's a little bit of, again, the loop. All right. Thank you, Peter.